Hello students, welcome to the EPG Pathshala. I am Ashok Goel from the Department of Physics and Astrophysics, University of Delhi. Today we will discuss motion in a non-inertial frame. So far we have considered motion in an inertial frame. Now we will consider motion in a non-inertial frame, specifically in a rotating frame like our own Earth, from the paper Classical Mechanics. After studying this module, you will be able to understand and learn to describe motion in a non-inertial frame, as I said, specifically in a rotating frame like our Earth, and you will learn about Coriolis force which arises due to the Earth's rotation. Just as the centrifugal force arises, so the Coriolis force is an effective force which arises due to the Earth's rotation and it plays an important role in the atmospheric circulation and in long-range ballistics. You will also learn about Foucault's pendulum, which demonstrates most beautifully the rotation of the Earth. We know that Newton's laws of motion are valid in an inertial frame of reference. The inertial frame of reference can be chosen to be the frame with fixed charge. If you are interested in describing the motion of a dynamical system on Earth, we will have to take into account the fact that the Earth constitutes a non-inertial frame. The Earth is in fact in a very complex motion with respect to the fixed star. But for our purpose, it is enough to treat the coordinate system fixed on Earth to be undergoing only rotation about its axis, whereas in actuality the Earth undergoes a complicated motion with respect to the fixed stars. We thus have to deal with non-inertial rotating frames of reference. Now, this description will also be convenient for the description of the motion of rigid bodies, which will be taken in subsequent units. So, let us consider a rotating coordinate system. Now, we will consider two sets of coordinate axes. One set of coordinate axes is fixed in an inertial frame, so an inertial frame, and one set of coordinate axes are fixed there. The other frame, which we designate as sigma rotation, the rotating frame, is a frame which is in arbitrary motion with respect to the inertial frame. It could be rotating with respect to the inertial frame, or it could have any other complicated motion with respect to the inertial frame. We will take the non-inertial frame to be a simply a rotating frame. The coordinates in the inertial or in the fixed frame will be designated as xi primes, or that is, the coordinates in the inertial frame will be designated with primes or as xi with a subscript fix, and in the rotating frame as simply xi or xi with a subscript rho. Let us consider a point P whose position vector is given. So, you have a point P whose position vector is given by a vector r in the rotating frame. Capital R is the position vector of the origin of the rotating coordinate system. It will be very clear if you refer to the figure. So, capital R is the position vector of the origin of the rotating coordinate system with respect to the fixed inertial frame, and then the position vector of a point P in the inertial frame is simply given by the sum of these two vectors, which is clear from the diagram which is shown. That is, this position vector of the point P with respect to the inertial frame, the r prime, is equal to the vector sum of capital R and small r, where capital R is the position vector of the center of mass of the rotating frame with respect to the inertial frame, and small r is the position vector of the point P with respect to the rotating frame. Now, if the frame sigma rotation undergoes an infinitesimal rotation d theta, the displacement of the point P, which is fixed in the inertial frame, will be described by dr in the fixed frame is equal to d theta cross r. And this is possible because we saw earlier that an arbitrary infinitesimal displacement can always be represented by a pure rotation about some axis. In this equation, the infinitesimal displacement dr is measured in the fixed inertial coordinate system x prime. The infinitesimal displacement takes place in time dt. Therefore, dr by dt in the fixed frame is equal to d theta by dt into r. If the angular velocity of the rotation is omega, which is equal to d theta by dt, then we have dr by dt, that is the velocity in the fixed frame, is equal to omega cross r. Remember, the point P is fixed in the rotation frame, and it is the coordinate system itself that is undergoing rotation. Now let the point P has a velocity in the rotating frame given by dr by dt with a subscript rot to specify that this is the velocity in the rotating frame with respect to the xi coordinate system. Thus, the rate of change of the vector r in the fixed system is given by rate of change of r in the fixed system is equal to rate of change of r in the rotating system plus omega cross r. Now, this result which we have obtained for the position vector r is in fact valid for any arbitrary vector. Any arbitrary vector being defined as a physical quantity that transforms according to the same rules as the position vector. Thus, for any vector A, the time derivative of A with respect to the fixed frame is equal to dA by dt, the time derivative of A with respect to the rotating frame plus omega cross r. We next see that the angular acceleration omega dot is invariant under this transformation. Now, rate of change of omega with time, thus d omega by dt in the fixed frame is d omega by dt in the rotating frame plus omega cross omega, where omega is a vector. And since omega cross omega vanishes, omega dot in the fixed frame is the same as omega dot in the rotating frame. Thus, the velocity of a particle p measured in the fixed inertial coordinate system is given by dr prime by dt in the fixed frame, that is the velocity in the fixed frame is equal to fixed frame plus dr by dt, d capital R by dt plus d small r by dt. Substituting for dr by dt in the fixed frame in terms of what we have done earlier, then dr prime by dt is equal to d capital R by dt plus dr by dt plus omega cross r. Or in other words, the velocity in the fixed frame is equal to v plus v rot, that is velocity in the rotating frame plus omega cross r. That is, the velocity with respect to the fixed axis is equal to the velocity of the rotating frame with respect to the inertial frame, namely v, plus the velocity in the rotating frame, that is v rot, plus a term omega cross r. Omega cross r is the velocity due to the rotation of the rotating frame. We will now discuss the Coriolis force. Now, force on a particle in the rotating frame can be obtained from the expression of Newton's equation of motion, which are valid in an inertial frame. Namely, F inertial, the Newton's law says that the force in the inertial frame is equal to mass into acceleration in the inertial frame, acceleration being the time derivative of velocity in the fixed frame. Now, we have seen that how the vector transforms. Therefore, dv by dt, which is a vector in the fixed frame, is equal to dy by dt, dv by dt plus dv rot, the velocity of rotation by dt in the fixed frame, plus omega cross di by dt in the fixed frame. We will first assume that the velocity of the rotating frame with respect to the inertial frame is constant. So we will first assume that the rotating frame is moving with a uniform velocity with respect to the inertial frame, which means the first term dv by dt is equal to 0. Now we can substitute for the second term from equation 17.7, and in the third term dr by dt fixed is substituted from equation 17.6 to obtain the force in the inertial frame equal to mass times dv by dt in the rotating frame plus m times omega cross r plus 2m omega cross v rotation. And since this is the force in the inertial frame, it can be written from Newton's law as mass into the acceleration into the inertial frame. Thus, for an observer in the rotating frame, the effective force on a particle is equal to the mass times the acceleration in the rotating frame is equal to mass times the acceleration in the inertial frame minus m omega cross r minus 2m omega cross v rotation, where a rotation is equal to dv by dt rotation. Thus, the effective force experienced by a particle consists of a term from Newton's law, a term a and m times omega cross r, which is the familiar centrifugal force term, which is equal to minus m omega square r, when omega is normal to the radius vector, and the negative sign means that the force is directed outwards from the center of the rotation. Now, in addition, if the particle is moving in the rotating frame, there also exists another force which is proportional to the velocity of the particle. Now, this force is known as the Coriolis force. In fact, the centrifugal and Coriolis forces are not forces in the usual sense. Nevertheless, the forces are real in the sense that one feels an outward centrifugal force if one sits on a merry-go-round, as all of you must have experienced. These forces can be dispensed with if we prefer to describe the motion of a dynamical system in the inertial frame only. So, if we describe the motion of a system in the inertial frame, then these forces don't come into play. They arise because we have chosen to describe the motion using Newton's laws in a non-inertial frame, in the present case a rotating frame, whereas Newton's laws are strictly valid only in a inertial frame. So, if we want to use Newton's law in a non-inertial frame, then we have to reckon with these forces. Thus, in order to write Newton's equation in the non-inertial frame, we need to add non-inertial terms in the expression of the force along with the usual force. So, the effective force is the force in the inertial frame plus the non-inertial terms, which in this case are the centrifugal and the Coriolis forces. The Coriolis force, like the centrifugal force, arises only in a rotating frame of reference. If, for example, we want to describe the motion of a particle under gravity on Earth, then in addition to the force of gravity acting on the particle, we will need to take into account the centrifugal force. The centrifugal force, in fact, counterbalances a part of the gravitational force, and over and above this, we have a Coriolis force. The Coriolis force associated with the Earth's rotation is quite weak because the Earth rotates about its axis only once in a day. This rotation of Earth once in a day corresponds to an angular speed which is as small as 2 pi times 10 to the minus 5 radians per second, So, to appreciate this, if an object is moving with a speed of 1000 meters per second, the maximum possible Coriolis force on it is of the order of 10 to the power minus 2 meters per second square, which when compared to the gravitational force of 10 meters per second square is 3 orders of magnitude smaller. So, Coriolis force may be weak, but it has an important consequence. On Earth, it acts to change the direction of a moving body to the right in the northern hemisphere and to the left in the southern hemisphere, as we have illustrated in this diagram, where omega is along the direction of the axis about which Earth is rotating, v is the velocity of the particle, then the Coriolis force acts as shown in the diagram. So, the centrifugal and Coriolis forces are responsible for large-scale atmospheric circulation in the development of storms and the sea breeze circulation. And furthermore, it is very important to incorporate Coriolis force in large distance flights and in long range ballistics. With the help of an example now, we will show the effect of Coriolis force. Imagine a gunner firing a shot in the northern hemisphere at a latitude of 45 degrees. The gun is fixed at an angle of elevation alpha towards the north, so that if the range is 20 km, the shell falls 44 meter towards east from the mark. And if the gun was fired in the southern hemisphere, the shot would have fallen 88 meter towards west. Set up the coordinates as shown in the figure. We'll take the z-axis along the line joining the center of the Earth with the point P on the surface from where the gun is fired. And the x and y axis are chosen such that the gun is fired in the yz plane and xyz form a right-handed coordinate system. The angular velocity omega has components along these three axes, as omega is equal to x component of omega is 0, y component is omega sine lambda, and the z component omega cosine lambda. The velocity of the shot makes an angle lambda with the y-axis and is in the yz plane. Therefore, the components of the velocity of the shot are x component is 0, y component is v cos alpha, and the z component is v sin alpha minus gt, because the acceleration along the z-axis is minus g. The effect of centrifugal force, which acts along the positive z direction, is to modify the acceleration due to gravity. With this then, the equation of motion becomes mr double dot is equal to minus mg, a unit vector along the z-axis, minus 2m into omega cross v. Now, omega cross v can be expanded, and we get the equation of motion along the x direction as mx double dot is equal to 2mv omega cosine alpha plus lambda plus 2mv omega g sine lambda t, and along the z-axis mz double dot is equal to minus mg. Equation can be easily integrated. We get x is equal to 2v omega cosine alpha plus lambda t square plus 1 by 3 v omega g sine lambda t cube. The time of flight is given by t is equal to 2v sine alpha by g, and the range of the projectile is given by d is equal to v square by g. Substituting for d 20 kilometer, lambda being 45 degrees, alpha is 45 degrees for the maximum range, and for g is equal to 10 meters per second, we get x is equal to 44 meter, where in this omega, the rotational velocity of the Earth is 2 pi into 10 to the power minus 5 radians per second. If the gun was fired in the southern hemisphere, in that case, x would have been minus 4 meters. Let us talk about Foucault's pendulum. Foucault pendulum is a heavy metal sphere suspended by a long wire. The suspension point of the pendulum is free to rotate in any direction. Now, the effect of the Coriolis force on the motion of this pendulum is to induce a rotation of the plane of oscillation. So, you have the pendulum is oscillating in a plane. The effect of the Coriolis force is to rotate this plane of oscillation. And in here, we will consider the motion of the pendulum at some altitude lambda and see how or with what velocity the plane is precesses. The coordinate axes are chosen such that the z-axis is along the local vertical. So, if I am doing the experiment here, I have a pendulum here at some latitude lambda. So, with the z-axis are chosen along the local vertical, the origin is chosen at the point where the pendulum is at rest in equilibrium. So, you hang the pendulum, so pendulum is at rest, so origin is chosen here and the xy plane are chosen in the horizontal plane. We assume the amplitude of oscillations to be small and we let T be the tension in the wire and the wire has a length small l. For small oscillation, the tension T can be resolved into components. The T has components along the x, y and z axis as minus T x by L along the x axis, minus T y by L along the y axis and T along the z axis. The tension provides the restoring force proportional to the distance along the x and y directions, whereas along the z direction is a constant force. The rotational velocity omega at the altitude lambda can also be resolved in components and has the components given in the equation 17.16, which are the angular velocity components along the x direction of the x component is 0, y component is omega sine lambda and the z component is omega cosine lambda. The Coriolis force produces small velocity components in the x and y directions and there is no motion in the z direction. Thus, the velocity has components along the x and y direction and the z direction is given in equation 17.23. The equation of motion of the Foucault pendulum can now be written as mr double dot is equal to mg plus t minus 2m omega cross v in terms of components where x double dot is approximately equal to minus t by m x by l plus 2y dot omega sine lambda, or x double dot is equal to minus omega naught square x plus 2 omega sine lambda y dot, and the corresponding equation in the y coordinate is y double dot is equal to minus omega naught square y minus 2 omega sine lambda x dot, where omega naught is under root t by ml. Now, these two equations for x and y coordinates can be solved by multiplying the second equation by I, adding the two equations, then we get equation in x plus iy, and in fact the equation looks like x double dot plus iy double dot plus omega naught square x plus iy plus 2i omega sine lambda x dot plus iy dot is equal to 0. Now, defining a new coordinate x plus iy as a new coordinate, the solution of this is of the form x plus iy is equal to eta e to the power minus I alpha t. Substituting this, the general solution then can be written as eta t is equal to e to the power minus I omega sine lambda t a e to the power I beta t plus b times e to the power minus I beta t, where beta is equal to omega naught square plus omega square sine square lambda under root. If the earth is not rotating, then omega is equal to 0, beta is equal to omega naught. That is, the pendulum oscillates with the frequency omega root naught is equal to under root t by ml. And for omega naught much greater than omega sine lambda, eta t is equal to exponential minus I omega sine lambda t into a e to the power I omega naught t plus b e to the power minus I omega naught t. By equating the real and imaginary parts, we can easily obtain the solutions for x and y. We see that over and above the oscillatory motion of the pendulum, the plane in which the pendulum oscillates also precesses with a frequency omega sine lambda, and this will complete one full rotation after a time t given by t is equal to 2 pi by omega sine lambda, and this demonstrates the proof of Earth's rotation. So let us summarize what we have learned in this module. We have learned that the centrifugal and Coriolis forces arise only in a rotating frame of reference. Viewed from an inertial frame, there are no such forces. These forces are experienced only in a non-inertial frame, in our case in the rotating frame of reference. Coriolis force is an inertial force. It is exerted on a particle moving with a velocity v in the rotating frame of reference and given by the Coriolis force F is equal to minus 2m omega cross v, where omega is the rotational frequency, rotational velocity of the frame, and v is the velocity of the particle in that frame.